In most capacitors, there is an insulating sheet of material such as a paper or plastic called a dielectric between the plates. So if we have a parallel plate capacitor and instead of the air or if we fill it with a material that helps store the charge better, that medium that is insert in between is called a dielectric medium. So this serves several purposes. First, dielectrics break down less readily than air. So air needs a lot of energy for the air to be broken. So higher voltages can be applied without charge passing across the gap. And the dielectrics allow the plates to be placed closer together without touching. So you can increase the capacitance by decreasing the distance. If you look at the equation, a higher capacitance can be achieved by decreasing the distance. So dielectrics are insulating the two plates. If we can narrow down the gap, we can increase the capacitance. Thirdly, it is found experimentally that if dielectrics fills the space between the two conductors, it increases the capacitance by a factor of K. So earlier we looked at the equation where no dielectrics were used. The general equation of the capacitance of any capacitor is given by its direct proportionality to area and distance of separation. As you can see, that capacitance is directly related to area and it is inversely proportional to the distance of separation. But in a new finding, when they found that if they can insert a certain type of material which enhances this process, they call that medium as dielectric. And the capital K that we use here is a dielectric constant. And different materials have different values for the dielectric constant. For example, air is 1, and there are many other surfaces that can be used. For vacuum, it is 1. For air also, we use, for air, the dielectric constant K is actually close to 1. It's 1.0006, and for vacuum, K of vacuum, it is just exactly 1. So there are other materials that can be inserted like paraffin, polystyrene, vinyl, paper. Even paper acts as a very good dielectric and has the dielectric constant of 3.7. And the dielectric strength means the electric field increases to 15 cross 10 raised power 6. So oil is also used as a dielectric for big capacitors, rubber, porcelain, all of these are dielectrics. Mica is also used, and sometimes liquid water. For example, an air-filled capacitor consisting of two parallel plates separated by a distance d is connected to a battery across with a voltage of V. So if this is the capacitor of capacitance C and this is the battery to which it is connected, and while it is still connected to the battery, a slab of dielectric material. So if I insert, while it is charged with the help of this voltage, a dielectric material is inserted whose value is K is equal to 3. So will Q increase, decrease, or stay the same? That's my question. Since the capacitor remains connected to battery, the voltage stays constant and equal to the battery voltage. The capacitance increases with the dielectric material is inserted because K has increased. So if K increases, capacitance automatically increases. From the relation Q is equal to CV, if capacitance is increasing, the charge will also increase. But even if V is staying constant, but if your capacitance is increasing, Q will increase automatically. So charge will increase if dielectric is inserted. As the dielectric is inserted, more charge will be pulled from the battery and deposited onto the plates of the capacitor, and that's how its capacitance increases as well. So what is the capacitance of two square plates? 6.6 centimeters distance between them. So D is given 6.6 centimeters or 6.6 cross 10 to the power of minus 2 meters. And the dielectric is filled with paraffin. So the dielectric or the capacitor is filled with a paraffin. I'm sorry, the distance between the two parallel plates is 1.8 mm, and it's the area that the sides are 6.6. What is the capacitance of two square? They are square actually, all the sides are same. So if you have square plates, so you may want to draw the diagram a bit differently. So two square plates with each side being 6.6 centimeters. 6.6 centimeters. This will help you get the area. And the distance of separation between the two is 1.8 mm, which is 1.8 cross 10 to the power of minus 3 meters. And assuming that this is also, you can find the capacitance if it's connected to a voltage source. So you have to find the capacitance. Basically, the capacitance, now that the medium is insert in it, so we have to put the K here because a dielectric medium has been insert. So paraffin, if you look in the table, in your textbook, the table gives the value of paraffin in table. For all dielectrics, please go to table 17.3 in your textbook, page 485. And it will give you the values for different types of materials that can be inserted. And for paraffin, it is 2.2. K is 2.2. So if we put the value of 2.2, epsilon naught is known, area can be determined, and the distance of separation is given to us. So it's a dimensionless quantity, and epsilon naught is 8.85 cross 10 to the power of minus 12 coulomb square, Newton meter square. And then area is 6.6 cross 10 to the power of minus 2 meters whole square. So you got to square that because the plate is squared. And the distance of separation 1.8 millimeters, that is 10 raised to power minus 3 meters is there. So go ahead and plug in the numbers in your calculator and find out the resulting capacitance. Make sure that you know the unit of capacitance, the SI unit of capacitance is farad, 10 raised to power minus 11 farads. So these are the values of several dielectrics, and dielectric strength is maximum field a dielectric can experience without breaking down. So if you increase the dielectric, after that it can break down. So mica is given as 7, and all other values are also there. Not only do we have dielectrics in our regular life, we also have in the molecular structure also we can experience the capacitance of a capacitor in the molecular structure as well. So it has long-term uses as well. So next we go ahead and talk about the molecules in a dielectric that tend to become oriented in a way that reduces the external field. So it's like if we have a material in between, and if this is positively charged plate and this is negatively charged plate, so the negatively charged ions will get pulled towards the electric field, and the positively charged ions will get more pulled towards the negative end, just like in polarization. And hence there is a charge separation happens. So what happens? There is a uniform electric field E due to these two plates, and the direction is this way. But because we have negatively negatively charged side this way, the electric field between this side and between positive of this and this is this way. On the other hand, the electric field between this minus charge and plus charge and this negative charge is also that way. So the net electric field reduces because of the because of this insert that we have done. So it actually, you need to subtract the electric field from here. So this is the, if you see, this is the initial electric field. This is also the initial electric field. And so when we say that the dielectric field actually got reduced because of the insertion of a medium, some of the electric field lines that do not pass through the dielectric but instead end on the charges induced on the surface. Hence, the electric field within the dielectric is less than that. The electric field here, if I assume this is E1 and this is E2, E2 is always less than E1. The electric field inside is less, and it's being reduced by a factor of K. So the voltage across the capacitor is reduced by the same factor K, because V is E times D. There's a relationship between electric field and voltage as well. If electric field is decreasing, the voltage will also decrease. So you got to understand these different figures. The figure A is just a simple capacitor when no dielectric is inserted. And figure B, because of the dielectric molecules will tend to become oriented. We also call them as a polarization. So they get polarized, and the negative sides line up close to the positive side, and the positive sides line up to the negative electrode on this side. So even if the dielectric molecules are not polar, electrons will within them will tend to move slightly towards the positive capacitor plate. So the effect is same. The net effect of the aligned dipoles is a net negative charge on the outer edge of the dielectric. So if you can look at, there's a net negative charge on this side and there's a net positive charge on this side. And hence there's a separate electric field created within the dielectric. And that's why when we take the sum total of the electric field, it seems to have diminished the effect of the electric field. So this means that electric field within the dielectric is less than it would be in air, allowing more charge to be stored for the same potential. So it stores, for the same potential you can store more charge, and hence that's beneficial. That's why dielectrics are important. Apart from that, we also have the capacitors can store energies. Capacitors are good energy storage devices, and they store the energy in the form of potential energy, which is given by 1/2 CV square, where C is the capacitance and V is the voltage. So So we can work on number 51, another problem. The electric field is, the capacitance is found with the help of the formula Q is equivalent to CV. So C, because now we know the formula of C is K epsilon naught A over D when we use a dielectric. So the plates separation is given, the dielectric constant is given, and the charge is also given to you. Determine the capacitance of this capacitor and the area of each plate. So you have to find the area as well, and you also have to find the capacitance. So first let's find the capacitance with the help of Q is equivalent to CV. Once we have the capacitance from this formula, we can then go ahead and find area with the help of this equation. So with the combination of equation 1 and equation 2, we'll be able to get both the variables. So C is equivalent to Q over V using this, and Q is 0.675 cross 10 to the power of 10 to the power of minus 6. There's a 5 here. Microcoulombs is 10 to the power of minus 6. So 0.675 multiplied by 10 to the power of minus 6 coulombs over voltage. We have been given voltage instead, but we know we don't have exact voltage or the potential difference given, but we know V is equal to E into D, because electric field is also a potential difference over the distance. So we can use E dot D in place. And therefore, we have the electric field given to us, 0.675 cross 10 to the power of minus 6 coulombs over electric field of 8.24 cross 10 to the power of 4 volts per meter. And the distance of separation is 1.95 millimeters. That is 10 to the power of minus 3 meters. So solving this, we end up getting the capacitance as C is given as 4.20 cross 10 to the power of minus 9 farads, which is a 4.20 nanofarads. In the same, now that we have capacitance, we can go ahead and use equation 2 to get the area. We'll rearrange the terms. When equation 2 is rearranged, we get area is equivalent to C multiplied by D over K epsilon naught. So substituting the values in here, we get the capacitance that we found, 10 to the power of minus 9, and D, the distance of separation, 1.95 cross 10 to the power of minus 3 meters. Sorry about the space here. Maybe we write a little bit more tiny. So rewriting area is C cross D over K epsilon naught, and C is the 4.20 cross 10 to the power of minus 9 farads multiplied by distance of separation, 1.95. (10 to the power of minus 3 meters) whole divided by K, where K is given as 3.75. Dielectric medium, epsilon naught is 8.85 cross 10 to the power of minus 12 Coulomb square over Newton meter square. So be very careful with the units, and in the end you should end up getting only meter square. So your area of the plates, after calculating carefully, is a 0.247 meter square. So there are many applications of capacitors. We find the capacitors have a tremendous amount of uses in binary numbers, in signal voltage, in signal voltages as well, TV and computer monitors, cathode ray tubes, and flat screens. All of them have a great use of electrostatics as well as capacitors. So we kind of wanted to look at what the electrocardiogram works like. The electrocardiogram detects heart defects by measuring changes in potential on the surface of the heart. This is the main application that we think will be good for biomajors to understand. Each time the heart beats, changes in electric potential occur on its surface that can be detected using electrodes. These are metal contacts that are placed near the heart and are attached to the skin. The changes in the potential are small, on the order of millivolts, and must be amplified. So they are displayed with a chart recorder on paper or on monitor in LCD. So electrocardiograms, and they are displayed with chart. These charts are studied, and ECG or electrocardiogram is the record of the potential changes. These are the potentials, and by now you know what is potential changes for a given person's heart. An example is shown here in this diagram, where We now look at the source of these potential changes and their relation to the heart's activity. These are the two heartbeats that have been shown. Both muscle and nerve cells have an electric dipole layer across the cell wall. And that is, in the normal situation, there is a net positive charge on the exterior surface and a net negative charge on the interior surface. So if you look at this diagram, under normal circumstances, the amount of charge depends on the size of the cell, but is approximately of the order of 10 raised per minus 3 coulombs per meter square of the surface. For a cell whose surface area is of the order of 10 raised per minus 5 meters square, the total charge on the surface can be of the order of 10 raised per minus 8 coulombs. So the story here is like heart muscle cell showing for the figure A shows a dipole layer in resting state. And this shows the depolarization of cell progressing as muscles begins to contract. And the figure C shows potential V at points P and P prime. So P and P prime. The P wave corresponds to the contraction of atria, and the QRS group corresponds to contraction of ventricles, as the depolarization follows a very complicated path. So in general, the knowledge of polarization, electric potential, all helps us to understand the science of ECG. The ECG is a very powerful tool in identifying heart defects. The right side of the heart enlarges if the right ventricle must push against an abnormally large load, for example, a clogged artery or blood vessels. This problem is readily observed on an ECG because the S wave becomes very large negatively. So I thought that it's a good idea to look at this example, and please go back and check the textbook to read this through completely. So the summary of the chapter, now that we have completed this chapter and the desired units were covered, what were recommended for your course, we looked into the electrical potential and the electric potential energy per unit charge. The relationship between the electric potential and electrical potential energy is given here. Then the potential difference, the electrical potential difference, that is also sometimes written as change in electrical potential, is minus E dot D. So, and then we worked on electrical potential, equipotential lines and electric field. Equipotential line is perpendicular to the electric field line. And we also looked into the electric potential at a certain distance from the source charge, and we found that electric potential at infinity is 0. And then the electric dipole we did not look into, so more complicated for your course. Capacitors, definitely yes, we looked into the capacitors and the relationship of Q and CV, and capacitance without a dielectric and with a dielectric. So